In this segment, we will consider limit laws, which are algebraic methods of working with limits. In the previous segment, we considered the concept of limit of a function and a finite number. But to work with that concept, we relied on tables or graphs. In this segment, we will consider methods that allow us to manipulate with limits rigorously. So the first thing that we will consider, we will discuss that limits can be combined using algebraic operations. Limits can be multiplied, divided, or raised into exponents. We will also talk about the existence of limits for some simple functions, for example, for polynomials, for rational functions, for trigonometric functions. Collectively, we will refer to these statements as the limit laws. It turns out that limit laws allow us to take a complex limit and break it into a combination of simpler limits. Then we evaluate the simple limits and combine the results to obtain the answer to the original problem. We will also consider limit laws that allow us to compare limits. These limit laws can be very helpful when proving existence of limits or when evaluating limits of functions that are not easy to manipulate with. Examples are trigonometric functions. Overall, limit laws provide tools for analysis of mathematical models and applications. They help us to both validate models and to make predictions based from the model. Our first group of limit laws is summarized on this slide. These laws can be proved rigorously, and in fact, if you are a math major, when you take a course on real analysis, you will be asked to prove each of these limit laws rigorously. However, for the sake of Calculus for Life Sciences course, we will accept these laws without a proof. However, many of these laws are very intuitive in nature. So let's take a look at the first one. It says that limit of a sum is equal to sum of the limits. And limit of a difference is equal to the difference of the limits. Indeed, that law is very intuitive. So if we know that function f is approaching value L and function g is approaching value M, then it is expected that their sum will approach value of L plus M, and their difference will approach value of L minus M. That can be observed on the graph, that can be observed from what we know about functions. Therefore, these laws are very, very intuitive. The second law states that limit of a product is equal to product of the limits. The third law states that limit of a fraction is fraction of the limits. Here we need to pay attention that our denominator does not turn into 0. Now, law number 4 says that a constant can be pulled out from inside of the limit. Because constant is independent of x, it does not reflect on existence of the limit. So another formula is number 5 over here. If we try to evaluate limit of a function raised into integer power, this is the same as to take the limit and raise the limit into the integer power. Similarly, when we take a radical of a function, we may as well take radical of a limit. Again, when we talk about radicals, we will assume that the resulting expression makes sense. In particular, if the power is even, then we will assume that the limit is positive or 0 so that we can safely substitute it inside the radical. Now, these laws do not specify what function we are looking at. And the only requirement that they make that both of the involved limits, there are limits that show up in the right side of these limit laws. The condition is that these limits should exist. If these limits do not exist, then these laws are not applicable. Also, because these first group of laws from 1 to 6 do not specify functions, I will call these laws the laws for algebraic manipulation. These formulas will allow us to take a complex limit and break it into a combination of simpler limits. However, the simpler limits still need to be dealt with. To help us with that task, the second group of laws is formulated below. These I will call limits of elementary functions. What are those limits? So in particular, limit of a constant is itself. That can be observed on the graph very easily. Similarly, limit of x as x is approaching a is equal a. It can be evaluated by substitution in this case. Similarly, if we have x raised to an integer power, positive integer power, then limit of x raised to n can be evaluated by substitution. Similarly, limit of a radical can be evaluated by substitution. In the second case, we will assume that a is positive if n is even to make sure that the expressions involved can be evaluated. Let us try to put some of these laws to use on the following example. Here I have graphs of two functions, f and g, given on the plot over here. The purple one is f and the orangey one is g of x. And I would like to compute the following limits. Let me start with this one. Limit as x is approaching -1 of the fraction f of x divided by g of x. It looks like the formula number 3 is the most appropriate formula for our case, and we can try to apply 3 to replace limit of a fraction with a fraction of the limits. So in the numerator, I will say x approaching -1 of f of x over here. And in the denominator, I will put limit as x is approaching -1 of g of x. Now, I'm taking a leap of faith, so to speak, because I don't know yet if the limits exist. If they do, and the denominator is not 0, then this step is valid. So for the time being, this step is in suspense. It's just I'm trying this step. Okay, nevertheless, maybe it's not too far to go to the conclusion. So let's take a look. -1 would be right over here. And f, in fact, has limit equals 0. So their limit in the numerator is 0. That is function f, and at -1, it has value 0. I put here that orangey, but maybe I should put a purple dot so that we have the same color dot as we have the graph. Okay, very well. Now we continue to the function g of x. The limit of function g of x at -1 is 4. It exists and it's not equal to 0, so that validates our step. Both limit exists and the denominator is not equal to 0. I can apply formula number 3. Now, once I apply for formula number 3, 0 over 4 equals 0, and that completes that first limit. Let me take a look at the second limit. The second limit says limit as x is approaching 2 of f of x minus g of x. And I look at the graph, and I see, okay, g of x is actually good. It's good at 2, it has value equals 0, it has limit equals 0. Let's write it down. So we notice that limit of g of x equals 0 as x is approaching 2. We also notice that g of 2 is equal to 0, all of the nice stuff. However, for the function f, we notice that the limit does not exist. And you can see it by observing that both left limit exists for function f and right limit exists. Let's write it down. So limit as x is approaching 2 from the left of function f, that limit is equal to 3, approaching from here. And limit as x is approaching 2 plus for function f of x, that limit is equal to 1. Left limit is not equal to the right limit, therefore limit does not exist in general. Guess what that means? That means that I cannot apply 1. I cannot apply 1 because at least one of the limits, this one, does not exist. All right, what to do? Does that mean we're stuck with this example? Well, fortunately, we can still look at one-sided limits, and all of the limit laws also apply to one-sided limits. So if we look at one-sided limits, we can observe that, okay, I'm running out of space here, so let me move a little bit to the right. Here, I took a fresh copy of the problem and I shifted everything a little bit to the right so that we can look at the solution more comfortably. So let's take a look at the limit as x is approaching 2 from the left of f of x minus g of x. Well, in that case, I know that limit as x approaching 2 from the left of f of x exists, and limit as x approaching 2 from the left of g of x exists. Both limits exist, so we could use formula 1 to replace limit of a difference with difference of the limits. The first limit as we approach from the left in function f is equal to 3, and g is 0, so that limit is 3. Absolutely the same way when we take x approaching 2 from the right. Both one-sided limits exist, so we can apply formula 1, and we can conclude that we're looking at limit as x approaching 2 from the right, f of x, minus limit as x is approaching 2 from the right of g of x. The first limit is 1, and the second limit is 0, overall 1. Now, these are one-sided limits of the difference. What about the total limit? Well, we can say since one-sided limits are not equal, we conclude that limit as x is approaching 2 of f of x minus g of x does not exist. Okay, I have to admit that's a little bit of an exotic example, but I wanted to highlight 2 things. In order to apply the limit laws, let me erase everything here. In order to apply limit laws, both limits must exist. If they don't exist, laws are not applicable. Now, in this case, we could not use laws to conclude that limit does not exist. We had to consider one-sided limits to go to the conclusion. In the future, we probably don't need to use this many detail when we solve examples with limits. A lot of things will come to us intuitive. However, this is the justification that you can produce if somebody will ask you for the proof. Let us look at the last example. We have a limit of a product of 2 functions, f and g. If we look at that limit as x is approaching 2 of f of x times g of x, we realize that function g does not have a limit. Limit of function f of x does not exist. As a result, formula 2 cannot be applied. Indeed, formula 2 can be applied if both limit of function f and limit of function g exist, and this one doesn't, so we cannot use it. However, we can try to look at one-sided limits. Let's take a look. We'll look at the limit as x is approaching 2 from the left of f of x times g of x. We know that one-sided limits exist for both f and g, therefore we can use formula 2 in this case for one-sided limits, and we will write limit as x is approaching 2 from the left of f of x times limit as x is approaching 2 from the left of g of x. The first limit is 3. The second limit is 0. 3 times 0 equals 0. Absolutely the same way, we will now consider limit as x is approaching 2 from the right. Again, I have function f of x times g of x. Both one-sided limits exist, so we can use 2. In fact, what we get is limit as x approaching 2 from the right of f of x times limit as x approaching 2 from the right of the function g of x. The first limit, when we approach x from the right, is equal to 1. The second limit is 0. 1 times 0 is 0. What about the existence of the overall limit? Well, according to our computations, both one-sided limits exist and they are equal. Therefore, we conclude that the limit overall exists and is equal to 0. Limit as x is approaching 2 of the product f times g of x exists and is equal to 0. So the answer over here is 0. This is a somewhat surprising result. One of the functions do not have limit, but product does. And we can establish it by considering one-sided limits. Importantly, we could not use formula 2 here to break into product of two limits. But we could use formula 2 for one-sided limits because both one-sided limits are defined for each function. Let us consider another example. Apply limit laws to evaluate the following limit, or state that limit does not exist. Okay, let's take a look. We have limit as x approaches 2 of a fraction, x cubed plus x minus 4 divided by x plus 3. The first applicable law is 3, and in a sense, we're taking a leap of faith because we don't know, maybe the process will get stalled and we'll go back. But for the time being, let us replace limit of a fraction with the fraction of the limits. So we will have limit as x is approaching 2 of x cubed plus x minus 4 in the numerator, and limit as x is approaching 2 of x plus 3 in the denominator. Both in numerator and in denominator, we will now apply formula 1. And in the numerator, we will write limit as x is approaching 2 of x cubed. We'll break into a combination of 3 terms. Now, the second term will be limit as x approaches 2 of x. And the last term will be limit as x approaches 2 of a constant 4. In the denominator, we have x is approaching 2. We're taking a limit of x plus limit as x approaches 2 of a constant 3. The last step will be to use a combination of the elementary limits. In particular, formula 7 tells me that the last term will be equal to 4, and the second term in the denominator will be equal to 3. The formula 8 tells me that the first term in denominator is equal to 2, and the second term in the numerator will be equal to 2. And finally, the formula number 9 tells me that the first term in the numerator will be equal to 2 cubed. The rest is simple. We just need to simplify the fraction. In the numerator, we have 8 plus 2 minus 4. In the denominator, we have 5. 8 plus 2 minus 4 is 6, so we have 6 over 5. Note that we make it a point to identify all of the formulas that we use. In the beginning, it's very important to realize that behind every step that we make, there is a mathematical formula that we use. If you cannot identify a mathematical formula that you used, that's a good indication of an error. Every step that we make is based on a formula, a theorem, a mathematical fact. So in this exercise, we took care to identify every formula that you use. As we solve more examples and we get more comfortable with solving limits, we will eventually stop referring to each individual formula that we use. But that doesn't mean that we stopped using the formula. We are still using that formula on the background. It did not go away. Let us consider a few more examples of evaluating limits using limit laws. And we will start by looking at a couple of special cases. One special case is given by this very special formula. We are looking for a limit as x is approaching a of a following fraction, x minus a divided by x minus a. We can graph that fraction, and what we will see, the graph will look like a horizontal line, y equals 1, except one point. We notice that we cannot substitute x equals a into the function because we will have division by 0. That fact is reflected by this empty circle that indicates that the function is undefined at x equals a. Nevertheless, its limit perfectly defined. That limit is equal to 1. And we will see that function in examples below. More generally, if we have two functions, f and g, given on these pictures, and we know that the functions are the same except for one point, or here at point A, there is a distinction. Function f has a nice solid circle right there on the graph. It's a very straightforward function. But for function g, instead of value that is on the curve, we have an empty circle, which means that that point is skipped on the curve. And the value of the function, in fact, something like 2.5. So g of a is equal to 2.5. Now, other than that particular point, the functions are identical. You can prove rigorously in that case that the functions will have the same limit. Indeed, value at the point A does not reflect on what limit function has or doesn't have. Therefore, if the functions coincide everywhere but one point, their limits will be the same, regardless what happens at that point. Let us use these facts to solve the next example. We are looking for a limit of the fraction x squared minus 4 in the numerator divided by x minus 2 in the denominator as x is approaching a. We notice that when x is equal to 2, the denominator turns into 0. Therefore, we suspect that we cannot use formula 3 just yet. We're not ready for it. For the formula 3, we need to make sure denominator is not equal to 0. So that is not the case. We cannot use it. Well, if we cannot use formula 3, what can we do? In fact, we have an indeterminate form of 0 over 0, and we need to reformulate that expression. We need to rewrite the expression in a determined form to proceed. And limit laws can help with that. Let's take a look. I start by copying the expression that we're trying to study. And one good point to start is to look if we can rearrange the expression a little bit. And we'll collect every possible fact that come to our mind. One fact that comes to our mind is that numerator can be factored. X squared minus 4 can be factored as x minus 2 times x plus 2. The denominator, I cannot do much. I just keep it as is. But then I notice, but wait a second, I have this x minus 2 over x minus 2. It turned out that that's a very important clue, and there are a couple of ways you can proceed. So let me give you one way to proceed, and then I'll give you another way to proceed. They are very closely connected, but they have slightly different flavors. Okay, so let me do this. So first of all, I will regroup the terms a little bit. X minus 2 over x minus 2, I will group together. And that x plus 2 from the numerator, I will put next to the fraction. And then I can use law number 3 and split into product of two functions and two limits. The first limit is a limit of x minus 2 over x minus 2. And the second limit, as x approaches a, is of x plus 2. Now, the claim is that we can evaluate both. In particular, according to what we discussed over here, that first limit is equal to 1. And to compute the second limit, we can use formula 1 and break into the sum. So we can say limit as x approaches 2 of x plus limit as x approaches 2 of 2. Again, I'm being very, very slow here, and I am mentioning every single formula that we used. In the future, we will speed up and we will just proceed through steps without showing every individual limit law that was applied. But for the time being, I would like to emphasize every step we make has a formula behind it. Well, we are almost done. 1 stays here, and a limit of x when x approaches 2, according to formula 8, is 2. And limit of 2, according to formula 7, is 2. So we have 1 times 4 equals 4. That would be the answer to the limit. So let me erase that, the indeterminate form thing. We are ready to write down the answer. The answer is 4. Okay, I told you that there is a couple of ways to proceed. So let me show you another way to proceed. When we notice that there is a factor, so let me start from copying the original expression. And the first step is the same. The first step is the same as x approaching 2. We factor the numerator and we copy the denominator. Now, another way to treat that special case, x minus 2 of x minus 2, is to notice that for the sake of discussing limits, we can exclude x equals 2. It is not important to consider x equals 2 at all when discussing existence of the limit. If x is not equal to, then these two terms cancel and they're equal to 1. These two terms can be evaluated. We can mathematically prove that as long as x is not equal to 2, that group of terms returns 1. So assuming we don't look at x equals 2, we can just cancel this term and replace this fraction with x plus 2. And then we can apply the laws and eventually conclude that the answer is 4. It is a very, very closely related approach to the first one. Nevertheless, it has a slightly different flavor. Let's see which one will be your favorite. Let us take a look at another example. Here we have a limit of the fraction. In the numerator, I have 2 plus h cubed minus 8. In the denominator, I have h. So if we substitute h equals 0, we observe that we have division by 0. Therefore, we are not ready to apply formula 3 and replace limit of a fraction with a fraction of the limit. The 3 does not work. No. Instead, we have to work out this expression and see if a simplification can be found. Okay, so the first thing I would like to start with, I would like to work on that cube. And I have a formula that I happen to remember, but if you did not remember that formula, you can obtain it by essentially multiplying a plus b 3 times and simplifying. The result will be a cubed plus 3a squared b plus 3ab squared plus b cubed. That's what you get when you completely expand the cube of a sum. And let me write this formula. So I have limit as h is approaching 0. In the denominator, I will have h. In the numerator, the 2 plus h cubed will be replaced with 2 cubed plus 3 times 2 squared times h plus 3 times 2 times h squared plus h cubed. That takes care of the 2 plus h everything cubed, and then I still have minus 8. Very well. We do have some simplification. Let me start writing it. So I copy limit as h approaches 0. And in the denominator, I will have h. There's not much I can do with it right now. But then I notice that 2 raised to cube is 8. And 8 will cancel with this 8. So 8 cancels 8, and the rest I just copy. So 3 times 2 squared, that is 12. 3 times 2 is 6. And h cubed. Very well. Well, actually did not need that much of a fraction line. What do we do next? Next, we will factor out h. So we'll have h, factor it out. Inside, we'll have 12 plus 6h plus h squared. And the denominator is h. And now, whichever is your favorite approach, we can say if h is not equal to 0, which is with completely right to say, because when h is approaching 0, we don't consider h equals 0 at all. We just see what's happening when h is close to 0 but not equal to 0. In that case, this h will cancel that h, and our expression becomes... Now, one last time, I will break this down into 3 limits, like limit as h goes to 0 of 12 plus limit h goes to 0 of 6h plus limit of h squared as h goes to 0. According to the formula 7, that first limit is equal to 12. Because 12 is a constant. According to the formula 4, and then 8, we'll have to use both of them. We will have 6 times 0. And the last limit, according to formula 9, is equal to 0. 6 times 0 is 0, so we have 12 as the final answer. Let us consider one more example. I have limit as t is approaching 0 of a fraction. In the numerator, I have square root of t plus 4 minus 2. In denominator, I have t. Again, I cannot use formula 3 because I have division by 0 in the denominator. Instead, I have to rewrite this expression to bring it in a more suitable form so one of these limit laws can be applied. The thing that I don't like here the most is the radical over here. And a way to treat a radical in the expression is to multiply and divide by a conjugate. So let me try that. I will keep limit as t goes to 0 here. But in the fraction, I will do the following. I will start with just the numerator. That's the term. And I will multiply it by the conjugate. It's radical of t plus 4 plus 2 over here. In the denominator, I will also put that conjugate. Notice that limit is still staying outside. We didn't really apply any limit laws yet. Okay, so let's see what kind of simplification we obtain. In the numerator, after multiplying to conjugate, we will have the following. T plus 4, that's the result of squaring the radical, minus 4, that's the result of squaring the second term. So one more time. So what do we use when we do this trick with conjugates? We use the fact that a minus b times a plus b is equal a squared minus b squared. Instead of a, I will have radical t plus 4. Instead of b, I will have 2, so radical t plus 4 squared is t plus 4, and 2 squared is 4. In the denominator, I will have t, and I also will have that conjugate term, radical of t plus 4 plus 2. We notice that the numerator simplifies, the 4 cancels, so we will have limit as t goes to 0 of t, and the denominator is t multiplied by the term radical of t plus 4 plus 2. And here we can say that as long as t is not equal to 0, which is something that we can assume because we're considering limit as t approaches 0, so 0 itself can be excluded from consideration. If we make that assumption, then these two terms can cancel, producing 1, and our limit can be replaced with limit as t goes to 0 of 1 over square root of t plus 4 plus 2. Now we can use formula 3. So now at that point I can say I can have formula 3. Why? Because denominator is no longer turning into 0. We can say we have limit of 1 as t goes to 0, that's the limit of the numerator, divided by the limit of denominator. So the limit of the numerator is 1. For the limit of denominator, okay, I'm starting to skip naming the formulas, and we kind of getting up to speed and how would we do it in a practical scenario. We would say, what happens to t? T goes to 0. So the expression inside the root will turn into 0 plus 4, and then we'll have plus 2. When we simplify, we'll have 1 over root 4 plus 2, which is 1 over 2 plus 2, which is 1 over 4. One thing that I forgot to mention is that using limit laws, we can establish something that's called direct substitution property. Direct substitution property applies to simple functions. For example, it applies for polynomials and rational functions. Rational functions are polynomial over polynomial. And what it states is that you can evaluate limit by substitution. So here we have limit as x approaches a. To evaluate that limit, it is sufficient to substitute a into the polynomial. For the rational functions, you can do it too, as long as the denominator is not 0 at a. Then limit of rational function can also be evaluated by substitution, like so. How can we see that? Well, let's take a look at the polynomial. A polynomial in the standard form looks like following. You'll have a coefficient b sub n that stands with the power of x raised to n, plus you'll have coefficient bn minus first that stands with the power of x minus 1. Then you will have a whole bunch of more terms, and eventually b1 that stays with x, and b0. Now, if we try to take a limit of the polynomial p of x as x is approaching a, we can start by using formula 1 and breaking limit of a polynomial, which would be limit as x approaches a of this entire sum, bn x raised to n plus bn minus 1 x raised to n minus 1 plus dot 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 plus b1x plus b0. We will replace it with the sum of the limits. The first limit will be as x approaches a, limit of bn or x raised to n, plus limit as x approaches a of bn minus 1 of x raised to n minus 1, plus dot dot dot, plus limit as x approaches a of b1x, and finally there will be limit as x approaches a of b0. Then we can apply a combination of law 4 and law 9 to compute each individual limit, and we will obtain bn times a raised to n plus bn minus 1 a raised to n minus 1 plus dot 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 plus b1 times a plus b0. And what it is, that's precisely value of the polynomial when x is equal a. In a similar fashion, you can establish the formula for the rational function, which I will leave as an exercise. Let us consider an application of the concept of limit to life sciences. Here we will look at the problem from the textbook about HIV prevalence and incidence. It turns out that in 1980s, a lot of people got sick with the HIV virus, and as we know right now, it's a RNA virus. But back in the day, very little was known about this disease, and the whole disease was surrounded by so much stigma that those people who got it early, they were doomed. There was no treatment for them. People were running away from them. It was very, very bad. And unfortunately, the disease flourished. It started to infect more and more people. And eventually, the doctors started to pay attention to it, and they started to look for treatments. Nevertheless, a lot of people got sick. In particular, San Francisco was affected and New York was affected. According to the data, the number of people affected by HIV in New York are well described by the following function. So the data can be fitted into a polynomial where t measures time in years since 1982. So how do I understand that? So here's a graph where the zeroth year is 1982, 1 year is 1983, 2 year is 1984, and you can continue. The function p is called the prevalence of the infection, and it counts the number of people that are infected at any given time. The incidence of the infection is the number of new infection per unit time over a specified time period. In other words, incidence is the average rate of change for the infection. So we have a few questions to answer. The first question is, what was the HIV incidence during the 12 months of 1983? So 1983, we have, this is where we started, and 12 months later, that would land us to 1994, and we would have to, the 12 months period converts into 1 year on the scale. So what we are looking for, we are looking at computing the number of new infections. Okay, here's the number of new infections. How we can compute number of new infections, we will take the number of infections at 1984, which is P of 2, and we subtract number of infections at 1983, which is P of 1. Here we go. That's the number of infections. And the time lapse is 1 in this case. So HIV incidence during the 12 months of 1983 can be computed by the following formula. P of 2 minus P of 1 divided by 2 minus 1, which is 1. And I already went and computed some of the numbers here. So P of 2 is 596, P of 1 is 217, and denominator is 1. When we simplify, we get 379 for the incidence during the 12 months of 1983. Very well. Let's take a look at the second question. What was the incidence during the first months of 1983? The first months would correspond to 1/12, and it's a little hard for me to say 1/12, but I would probably say somewhere here. So we would have to just make 1 month. I am approximating 1/12 to be just that little portion. So what will be the value of the prevalence? The prevalence will be P of 1 plus 1/12. I could, of course, combine it into 13/12 or even give you non-lead decimals, but I would like to highlight how it is obtained. We're starting with point at 1, the value of the time 1, and we move 1 month, which is 1/12. So 1 plus 1/12, that would be 1 month later. Okay, so HIV incidence during the first months of 1983 is equal to the following. We will take P at 1 plus 1/12. We subtract P of 1, and we divide by the time difference. The time difference in 1/12. Again, we can substitute the numbers, and according to my computations, what we should get something like 268.083333. Very well. Let's take a look at the last question. So the last question says, compute the limiting value of the incidence as the time interval shrinks to 0. So now we'll look at the following. We'll look at the time that is very small. Let me take some h. And we make a small increment in time. So we will have p plus h. That's the value, short period of time after the beginning of 1983. And we will compute value at the beginning of 1983, and we will divide by the time lapse, which is h. So that is the expression that we obtain by taking the incidence at 1983 for an arbitrary interval in time. If h is 1/12, you get the second case. If h is equal to 1, you get the first case. Okay, and what the third question is asking, what would be the limit of this expression as h approaches 0? Well, we can use limit laws to answer that question. Okay, I'll start here by copying limit as h goes to 0. And I will make a very long fraction line because we will have a very lengthy expression here. Instead of p evaluated on 1 plus h, this is what we will write. We'll say 80 plus 16 times 1 plus h plus 121 multiplied by 1 plus h squared. Okay, that takes care of the first term. And the second term, I already know, it's 270. Denominator is h. Very well. So we try to simplify the expression a little bit. So in particular, let me put it on the side because there's a lot of stuff written here. I want to simplify my life a little bit. So I'll put 121 multiplied by 1 plus h squared. 1 plus h squared, so let me keep 121. 1 plus h squared is equal to 1 plus 2h plus h squared. When 121 is distributed, I'll have 121 plus 242h plus 121h squared. And that will be substituted over here instead of this whole group. Okay, so let me copy my expression one more time. It will get worse before it gets better. Let me give it a shot. So 80, I'll copy. 16 multiplied by 1 plus h. I will distribute. I'll put 16 plus 16h. That's the result of distributing 16 in. And finally, I will put this whole three terms, 121 plus 242h plus 121h squared. That takes care of the first term. And the second term is 217. Very well. So now we can simplify it a little bit. Notice that 18 plus 16 plus 121 will make 217. Indeed, 18 plus 16 is 96 plus 121. So 6 plus 1 is 7. And 12 plus 9 is 21. So here we go. 217. And these three numbers, we can cancel that number. 16h can be combined with 242h. And 121h squared will not be combined with anything. It will pretty much stay the same. So what I'm going to do next, I'm going to shift things a little bit to the right so that I can continue working. Let me continue writing this expression. So I'll have limit as h approaches 0. In the denominator, I'll have h. In the numerator, I have 16 plus 242. It gives me 258h plus 121h squared. That can be simplified a little bit as limit as h approaches 0. What I will do, I'll factor out h. I'll have 258 plus 121h multiplied by h, and the denominator has also h. And then we notice that this h and this h can be cancelled. And the final limit looks like so. Limit as h goes to 0 of 258 plus 121h. Well, what's going to happen here? We will have h going to 0. So let me change the color here. H goes to 0. Therefore, in the limit, we'll have 258 plus 121 times 0, which means that the second term drops out, and we just have 258. Next, we will consider a few additional properties of the limit, and we will discuss something that's known as the squeeze theorem. First, we will recall the theorem 10, which says that one-sided limits and the limits at the point have connection. The limit exists if and only if both one-sided limits exist and they are equal. That is a fact about limits, and it's part of the limit laws. Then we will introduce a theorem where the functions are compared. In particular, if function f is less than or equal to g of x, and it's true on an interval that contains the point a, except maybe at point a itself, then you can prove that if we take limit of the function f of x as x approaches a, and take a limit of the function g of x as x approaches a, the inequality persists. If f is less than or equal to g, then limit of f will be less than or equal than limit of g. And here's an illustration for the theorem. So f of x, that would be function in green. And g of x, that would be function in blue. And g of x is greater than or equal to f of x. And you can see that their limits still respect the same inequality. Limit of f of x at 0, if we look at the limit as x is approaching 0, limit of f of x will be less than or equal to the limit as x approaches 0 of g of x. An interesting remark. Some people ask, what if the inequality is strict? What if the inequality is strict? Does that mean that when we go to the limit, you will have strict inequality between the limits? And the answer is no. Strict inequality does not convert to strict inequalities in the limits. And if you would like to have a simple example, consider x squared and x cubed on an interval from negative 0.5 to positive 0.5. If we look at the graphs, that we will see that x cubed will look something like this. So this is negative 0.5 and this is positive 0.5. Then y equals x cubed will look something like this. But x squared will be, well, higher. Because for small numbers, when you raise it to exponent, you get lesser result. So we notice that at 0 they are together, but as long as x is not equal to 0, x squared is strictly greater than x cubed. So the condition of the theorem are satisfied with a strict inequality. Nevertheless, if we look at the limit as x approaches 0 of x cubed, and if we look at the limit as x approaches 0 of x squared, both limits will be equal to 0. So here's a simple example that shows that strict inequality does not convert to strict inequalities when you take the limit. A very important theorem in calculus is the squeeze theorem. And the squeeze theorem states the following. Suppose we have an inequality that holds for three functions. We have three functions, f of x, g of x, h of x. and the inequality holds for them. It can be strict, it can be not strict. I will use the non-strict inequality. And that inequality holds for an interval that includes a. So here's an illustration. So this function in blue, that would be the h of x. That's the largest of all three functions. That function in purple at the bottom over here, that would be the f of x. That's the smallest of the three. And the function in the middle, that is between the two, that would be the function g of x. So what the squeeze theorem says, it says that if limit of the top function and limit of the bottom function exist and are the same. Suppose limit of the bottom function here, f of x, as x is approaching a, is equal to L, and the same limit is for the top function. So h and f, they meet, like here. They meet. When x goes to 0, the top function and the bottom function meet. They have the same limit. Then the middle function, the one that is squeezed between them, it has no other choice than also have a limit, and that limit will be exactly the same as the limit of the top function and the bottom function. So limit of g of x exists, and it is equal to L. It's a very important technical result in calculus because it allows us to prove existence of limits of functions that are not easily accessible to manipulation. Even on this graph, I made the function g oscillate wildly to suggest that that's a complicated function. And instead of studying the complicated function, thanks to squeeze theorem, we can replace the question with the question about simpler functions. H is simpler and f is simpler. Yet they allow us to make a conclusion about the limit of the complicated function g. Now, the difficulty with squeeze theorem is to have that inequality. That inequality is usually not easy to obtain. Sometimes it jumps at you, sometimes you need to look for it. So in the following, we'll consider a few examples that uses the squeeze theorem, and this inequality will be the centerpiece of it. And you will see that sometimes you can guess that inequality fairly straightforward, but sometimes it's not very easy inequality to obtain. So the difficulty of finding the limit with the squeeze theorem falls on constructing that inequality. If you have that inequality, you can apply squeeze theorem and compute the limit. But that inequality, in general, is not easy to figure out. Nevertheless, for the sake of this course, we'll give you a few simple things that will help you to solve the problems that are expected of you. And for the more complex, I hope to meet you in more advanced mathematics. So let us consider an example in which we will apply squeeze theorem to compute a limit. Here I have a limit of a function, x multiplied by cosine of 1 over x. So here's the graph of cosine of 1 over x. It oscillates wildly. When x goes to 0, it oscillates. Now, we do know that limit of cosine of 1 over x as x approaches 0 does not exist. Okay, but we don't have cosine of 1 over x. We have x times cosine of 1 over x. The graph is that green line. That is the graph of x times cosine of 1 over x. And the question is, does the limit exist for the new function when we multiply by x? One way to answer that question is to use the squeeze theorem. But for the squeeze theorem, we need an inequality. And we need not just any inequality, but inequality in which top function and bottom function meet. So can we come up with an inequality for this example? Well, let's take a look. So one of the things that we know about cosine of 1 over x, it is strictly between 1 and negative 1. And let us just focus for the time being on values of the x strictly greater than 0. So we will look at limit at x approaching 0 from the right. So we will only look for one-sided limit. Okay, let's start with one-sided limit. The squeeze theorem holds for one-sided limits too. I forgot to mention that, but it does. And we can try to see if we can come up with an inequality that will help us to take the limit as x approaches 0 from the right. Well, that inequality is sort of seen from the little facts that we know about cosine. If we multiply this inequality by x, we multiply the entire inequality by x. If x is positive, then the inequality stays the same. So I can write negative x less than cosine of 1 over x times x less than x. I have an inequality. X times cosine x is squeezed between x on one side and negative x on the other side. And that is what you see on the picture. This top line is y equals x. This bottom line is y equals minus x. And what's most important, if we look at the limit as x approaches 0 from the right, we will notice that x will go to 0. And negative x, it will also go to 0. When both sides of the inequality go to the same limit, that is when the squeeze theorem can be applied. By the squeeze theorem, the function in the middle has no other way as also to have a limit, and that limit will be the same as for the function on the left and on the right of inequality. Now, in a similar fashion, I will not talk about it here, but we can kind of extrapolate. In a similar fashion, we can show that if we take limit from the left of x cosine 1 over x, it will also be equal to 0. And then, since one-sided limits both exist and both equal to 0, we conclude that the limit in general exists and is also equal to 0, since both one-sided limits exist and are equal to 0. Let us consider one more example of using the squeeze theorem. Here we have a problem. Suppose it is known that the function f of x satisfies the following inequality on an interval from -1 to +1, except maybe at 0. The following inequality is true. And the problem says, use that to evaluate limit of function f of x as x approaches 0. When you see an inequality like that, when you have a function in the middle and there is another function on the left and another function on the right, that should ring a bell. Most likely, we are going to need the squeeze theorem, because that function on the left and the function on the right, they squeeze function f in the middle. Let's take a look. Let's start with the inequality. On the left, we have cosine x minus 1. Then we have inequality sign f of x. And then we have the x squared. So when x is approaching to 0, that's the limit that we need to evaluate when we need to evaluate limit as x approaching 0. As x approaches 0, what can we tell about the right side? Well, we know x squared will go to 0. That's a very simple limit. Limit of x squared as x goes to 0 equals 0. Now, what about cosine of x minus 1? Limit as x goes to 0 of cosine x minus 1. It turns out, and we will show it very shortly, cosine will approach 1 when x approaches 0. And 1 stays the same, So we'll have 1 minus 1 equals 0. Guess what? Cosine is also approaching 0. By the squeeze theorem, since limit as x approaching 0 of cosine x minus 1 is equal to the limit as x approaching 0 of x squared, and both are equal to 0, then limit of the function f of x as x approaches 0 also exists and must be equal to the very same limit. So here we go. We don't know what function f of x is. We don't know what the graph looks like. But squeeze theorem tells us we know the limit as x approaches 0. That limit is the same as the limit of the functions on the left and right. In fact, I went ahead and prepared a little illustration for this problem. Let me copy it over here. So the purple function is the function x squared. That's y equals x squared. That's the one that on the right side of the inequality, the largest one. The green function is y equals cosine x minus 1. That's the function on the lower part of the inequality. Now, function f, I don't know what it is. It can be anything. But what I do know, at any given time, it is squeezed between x squared on the top and cosine minus 1 on the bottom. So when cosine minus 1 and x squared meet at x equals 0, their function f is also still between the two of them. So it also has to go to 0. This is how we know that limit of function f of x is 0 without knowing the function. Squeeze theorem can be used to establish trigonometric limits. Theorem 14 states that limit of sine of t as t approaches 0 is equal to 0, and limit of cosine of t as t approaches 0 is equal to 1. Sine and cosine are both examples of functions that are not easy to manipulate with. Therefore, squeeze theorem becomes a very convenient tool. The trick to establish this theorem is to find a clever inequality, which we will consider very shortly. However, the result of theorem 14 can be used to prove the result of the theorem 15. And that result is essentially a substitution theorem. It says that to evaluate limit of a trigonometric function at a point, we just substitute the point in. It's a very important result. It allows you to compute limits of trigonometric function very easily. You just substitute the value for the variable. As long as the point in the domain of the function, tangent, secant, particular suspect, but as long as tangent can be evaluated, limit of tangent at that point is equal to its value. What we're going to do next, we're going to prove the theorem 14, and we will prove one statement in theorem 15. And if you would like, you can skip forward to the next theorem about special trigonometric limit, and then to a few examples where we work out trigonometric limits. Nevertheless, for those who are curious, I'm going to go through the proof of theorem 14 next. We would like to use the squeeze theorem to establish that limit of sine of t as t approaches 0 equals 0. The difficult part of using the squeeze theorem is to come up with a useful inequality. In the case of this limit, inequality obtained from a geometrical consideration. Let's take a look at the following chart here on the right. We will start from a unit circle. So that arc corresponds to a unit circle. The fact that the circle has radius 1 is indicated over here. The length of that radius is exactly 1. We then will mark an angle of exactly t radians, and it measured from the x-axis to that. Now, how do you measure an angle of t radians? And the way to measure an angle of t radians is to take a unit circle and measure distance of t units on its circumference. So, in other words, that arc from A to C, it is exactly t units long. That will measure angle of t radians. As you notice, I only focus on positive values of the angle, so I'm only looking at the top portion of that diagram. Now, it's time to put some geometrical considerations in. This is point C on the x-axis, and this is point A on the circumference. And from point A, we put a height, a line that's perpendicular to the x-axis, and the point where the line intersects the x-axis we will call B. Note that origin A and B make a right triangle, and the horizontal leg is exactly cosine t long, and the vertical leg, the AB, is exactly sine t long. Now, if we connect A and C with a straight line, we form another right triangle, ABC, and AC is the hypotenuse. So we can do some computations, and the hypotenuse will come out as square root 2 multiplied by square root of 1 minus cosine t in length. That's the hypotenuse. That's the length of the line AC. Now, from geometric considerations, we know that AB is a leg of a right triangle ABC. AB is over here, it's a leg of right triangle ABC. And the leg of a right triangle is shorter than the hypotenuse of the right triangle. AC is the hypotenuse, and it's guaranteed to be longer than the leg. Now, AC is the hypotenuse, and that's the line connecting A and C, and that's the shortest way you can travel from A to C. Another way you can travel from A to C is along the arc, but that would be longer. So here we go. Arc is longer than secant AC, the line. Very good. That's the geometrical inequality. AB is guaranteed to be shorter than AC, and AC will be guaranteed to be shorter than arc AC. Now, let's bring their actual length. As we discussed, AB is equal to sine t. That's the guy. AC can be computed as square root 2 multiplied by square root of 1 minus cosine t. And arc AC is equal to t. It is exactly t unit long. Substituting the actual measurements, we arrive at the following inequality. Sine t, it's a non-zero value, so it's going to be strictly greater than 0 for positive angle. That would be AB. Then AC is replaced with square root 2 multiplied by 1 minus cosine t. And finally, arc AC is replaced by t. We have our inequality. Now, I would like to emphasize that that inequality only holds for positive values of the angle t. But we are almost done. Let us consider a portion of the inequality. We'll carry out 0. We'll carry out sine t. We will skip the third part and we will jump straight to the fourth. So we'll have a simpler inequality. Let's take a look at this inequality. So sine t is strictly greater than 0 and t strictly greater than sine t. And this is true for t greater than 0. Now, what is going to happen when t starts to approach 0 from the right? Well, 0 is going to stay itself. T will approach 0. By the squeeze theorem, there's nothing else for sine t to do as also approach 0. Therefore, by the squeeze theorem, we conclude that sine t will approach 0 as t approaches 0 from the right. Now we can work with the lower portion of the picture of that graph above, and we can conclude that if we look at the limit as t approaches 0 from the left, we will have the same result. Limit of sine t as t approaches 0 from the left will also be 0. Combining the two, we can prove the limit in general. Then two-sided limit as t approaches 0 of sine t is equal to 0. Now we have a second statement that we need to prove, that the limit as t approaches 0 of cosine t is equal to 1. And there are two ways to do it. In principle, we could use the different portion of the inequality. We carry over 0, we carry over that square root, and we carry over t, and we can use the squeeze theorem. However, we can use a more powerful result. We can use the identity. We can use the identity, the sine squared plus cosine squared equals 1, and we can just compute the limit using the limit laws. So let us take a look. So I am looking at the limit of cosine t as t approaches 0. According to the identity, I can replace cosine t with the square root of 1 minus sine squared t at t approaches 0. And then we can use the limit laws. So in particular, limit of a square root is the square root of the limit. So I can put the limit inside. Limit as t goes to 0 of 1 minus sine squared t. Okay, very good. Then I can distribute the limit in. I can say that is equal to limit of 1 as t goes to 0, which is trivial, it's just 1, but nevertheless, we distribute the limit. And the second term will be limit of sine squared t. Let me correct that square root so it looks a little bit more natural right here. And then I realize that the first term is just 1, but the second term is this. We can put limit inside the square, and we will have limit as t goes to 0 of sine t. And we just established that that limit is 0, so we're looking at 1 minus 0 squared, which is overall equals 1. Here we use limit laws and the limit we just established to establish the second step. In theorem 15, we state that limit of the trigonometric function can be evaluated by substitution. What we're going to do next, we're going to show how to establish one of the statements, and the rest can be proved similarly. There are different ways to approach it. One way is to use trigonometric identities. In particular, sine of a plus b is equal to sine a times cosine b plus cosine a times sine b. We can use that identity to evaluate that limit. Let's give it a try. So we would like to compute limit as t approaches a of sine of t. Now, the first trick is to change the variable of the limit. We can introduce y, which is equal to t minus a. Or you can say t will be equal to y plus a. Either way, it's true. And we notice that y goes to 0 if and only if t goes to a. If t goes to a, y will go to 0. If y goes to 0, through this formula, t will have to be equal a. So if that's the case, then we can replace limit as t goes to a with limit of y going to 0. And instead of t, we will now write y plus a. So we completed the substitution of variable in the limit. T equals y plus a. Every time I see t, I put y plus a. And every time I see t goes to a, I can now put y goes to 0. Very good. So let me continue. We're almost done. Let me shift to the right so that we can finish that exercise. So now it's time to use the trigonometric identity. I'll have limit as y approaches 0 of sine of y times cosine of a plus cosine of y times sine of a. We can use limit laws to distribute limit on each of the term, obtaining the following. Limit as y goes to 0 of sine y, that's our first term, times limit as y goes to 0 of cosine a, plus limit as y goes to 0 of cosine y, times limit as y goes to 0 of sine a. Now, cosine a is a constant, so it's independent of y. The limit of cosine a is itself. However, when you say sine of y as y goes to 0, we know that limit is equal to 0. So the first term becomes 0 times cosine a. For the limit of cosine y as y goes to 0, we know that limit is 1. And sine a, it's independent of y, so the limit is itself. We'll have 0 times cosine a plus 1 times sine a. The first term goes away, and 1 is simplified to obtain the answer, sine a. And that's exactly what we're trying to prove. Let us consider one more application of the squeeze theorem to establish the special trigonometric limit. The special trigonometric limit consists of limit of a fraction sine t over t as t approaches 0, and the value of the limit is 1. Why is this limit special? This limit is one of the rare occasions when polynomial functions, which is t in the denominator, meets trigonometric function, which is sine t in the numerator. In general, it's very difficult to establish any relationship with polynomials and trigonometric, and here is one of those rare cases. Because of its importance, that limit was called special trigonometric limit. What we are going to do next, we will prove that limit. The proof itself is optional, so if you would like, you can skip that portion and jump to the place where we start working out specific trigonometric limits. In the meantime, let us start with the proof. As we said before, we will try to use squeeze theorem, and squeeze theorem needs a clever inequality. And in this case, the inequality can be obtained by making a geometrical argument. Very, very similar to what we did before. So what we're going to do, again, we will look at the positive angle of t radians. We will consider unit circle. So here the outside radius is 1. And we will measure angle of t radians. When we measure angle of t radians, we'll get that vertex A, and arc AC is exactly t unit long. Very well. From point A, we will put a vertical line, and when that vertical line crosses the x-axis, we'll put point B. From point B, we will use that segment OB as a radius to make another circle. And when that circle will intersect with the radius OA, we will put point D. Just in case the length of the side AB is sine t, we can compute that from the right triangle OAB. And the length of OB is cosine t, so all of the lengths we can compute from geometrical considerations. Now, what we're going to do next, we're going to look at the geometrical objects that we obtained from this figure. The first object for us will be the area of a sector OBD, right here. that sector sits inside the triangle OAB, and the triangle OAB sits inside the biggest sector OAC. Okay, I made a little mess here, so let me erase all of this. But we have three figures, one embedded into another and two embedded into the third. The smallest sector ODB sits inside the triangle, and both smallest sector and the triangle sits inside the largest sector. Because of that embedding, we know that area of the sector OBD, that's this sector over here, is less than the area of a triangle OAB, because the sector is inside of that triangle. It gotta be smaller or equal, but definitely not larger. And both two areas are smaller than the area of the sector OAC that includes both of them. Okay, that's just relationship between areas. All comes from geometry. Next, we will replace the areas of geometrical figures in this inequality with their corresponding expressions. Area of a sector turns out to be the angle times radius squared times 1/2. That's area of a sector. So angle is t right here. The radius for the smaller circle is cosine t. So I get 1/2 cosine t squared times t. Very good. Now let's take a look at the triangle over here. The triangle OAB. Area of a triangle is width times height times 1/2. So here's 1/2. Here's the width. Here's the height. That's area of the triangle OAB. And finally, for the largest sector, again, I'll have 1/2 times radius squared. Radius is 1 in this case. And t is the angle. T radius. Long story short, we have an inequality that ties together cosine, sine, and t. Now let us take this inequality 1/2 of cosine t squared t less than 1/2 of cosine t sine t less than 1/2 of 1 squared times t, and simplify. The first thing I'd like to do, I'd like to multiply by 2. When we multiply all three sides by 2, we will have cosine t squared times t less than or equal to cosine t sine t less than or equal to t. The 1 squared is 1, so we don't see it, and 1/2 has been multiplied by 2. Next, we will divide by t. So when we divide by t all three sides, noting that t is strictly greater than 0, we are not at t equals 0, we're just getting close to it. So that's possible. This is what we will have. Cosine t squared less than or equal to cosine t times sine t over t less than or equal to 1. And finally, we will divide by cosine t. Once we divide by cosine t, in the left side we'll have cosine t. We had squared, we divide by cosine, 1 cosine goes away, 1 cosine stays. And in the middle term, the cosine t will cancel, so we'll just have sine t over t. And the last term will become 1 over cosine t, which brings us to this inequality. We are almost done. So let's look at that inequality. Let me copy it over here. Cosine t less than or equal to sine t over t less than or equal to 1 over cosine t. And let us remember that we are looking at the case t greater than 0. And that means that we will be considering taking a limit of sine t over t as t approaches 0 from the right. Nevertheless, we can take a look. The limit of cosine t as t approaches 0 from the right and from the left in general is equal to 1. So I know that term will go to 1 as t goes to 0 plus. Now, what about 1 over cosine? Well, according to limit laws, we can replace limit of a fraction with a fraction of the limit. We can say 1 over limit of cosine t as t goes to 0. And we know that cosine t is approaching 1, so we'll have 1 over 1 equals 1. So guess what? The term on the right also approaching 1 as t goes to 0 plus. By the squeeze theorem, limit of sine t over t as t approaches 0 from the right is equal to 1, which brings us to this result. Now we can do the same reasoning, but we can focus on the low portion of the diagram above, and we can prove the similar result for the case when t is approaching 0 from the left. Then we can combine the two results to prove the limit in general. In conclusion, we will consider a few examples of evaluating trigonometric limits. We will now use all of the facts that we've learned to evaluate the limits. Our first example is limit as t approaches 0 of a fraction, tangent t over t. When we see a fraction that mixes up trigonometric functions and polynomials, it should immediately ring a bell. We will have to use special trigonometric limit, because we see that trig functions meet polynomials. So let's take a look. The special trigonometric limit is as t goes to 0 of sine t over t equals 1. Now, I don't see sine t over t, I see tangent. What can we do? Can we rewrite that expression so that special trigonometric limit can be seen clearly? Yes, we can, and in fact, it's not very hard. We notice that tangent is sine over cosine, and then we have a mixed fraction, which we can simplify as limit as t goes to 0 of sine t stays in the numerator, t stays in denominator, and cosine t will go into denominator. So now we start to see what's happening. We can break this into product of two limits. The first limit is sine t over t, and the second limit is 1 over cosine x as t goes to 0. And the first limit is 1, and the second limit can be replaced with the 1 over limit cosine x as x goes to 0. So you'll have 1 multiplied by 1 divided by 1, altogether 1. Let's take a look at another example. We have limit as t goes to 0 of cosine t minus 1 divided by t. Again, I have a mixture of trigonometric function and polynomial functions. We expect to use special trigonometric limit. Not that you will need it every time, but every time you see that polynomials meet trigonometric, it suggests that maybe that limit will be important here. So you just start thinking about possibilities of using it. Okay, nevertheless, the special trigonometric limit is limit as t goes to 0 of sine t divided by t equals 1. And we don't have sine in that expression regularly. We have cosine. So how is it possible to convert cosine into sine? One way to do it is to use the identity that sine squared t plus cosine squared t equals 1. And in particular, sine squared t can be traded for 1 minus cosine squared t. And 1 minus cosine squared t can be factored as 1 minus cosine t, 1 plus cosine t. And now we see, wait a second, but we have this cosine t minus 1. Does that ring a bell? Well, the suggestion is to multiply by a term that is matching it and bring it over here. So in particular, I don't want to call it conjugate, but it is sort of conjugate for this particular meaning. So we will start with copying our expression. In the numerator, we have cosine t minus 1, and denominator we have t. And we will multiply and divide by cosine t plus 1, both in the numerator and denominator. Okay, let's simplify. In the numerator, we will have cosine squared t minus 1. And in the denominator, we'll have t multiplied by cosine t plus 1. Okay, very good. The numerator simplifies to, okay, so 1 minus cosine squared t is sine t, but cosine squared t minus 1 is negative sine t everything squared. And the denominator is t multiplied by cosine t plus 1. And we are almost ready. So let me rewrite the expression in the following form. So the sine t, I know that is sine t times sine t because I have the square. So I will use 1 sine t to group it with the t in the denominator. Then 1 negative sine t I will keep here, so it has a negative. And the cosine t plus 1, I will just keep it out. Now we can take the limit. We know that these two terms approach 1. This first term approach 0, that negative sine t in the numerator, and cosine approaches 1. So when we take the limit, when we send t goes 0, we'll have 1 multiplied by, in the numerator we'll have 0, in denominator we'll have 1 plus 1. When we combine all of the numbers, we'll have 0. Let us take a look at another example. So here we have limit as t approaches 0 of a fraction sine 3t divided by 2t. And we already know when polynomials meet trigonometric, their idea is to use special trigonometric limit, which is limit as t approaches 0 of sine t over t equals 1. Now, I have something that looks very, very similar. In particular, that 2 in the denominator can be factored out. I can put it up front. 1/2 of limit t goes to 0 of sine of 3t. And this 3t sits inside sine divided by t. And I realize that it looks similar but not the same. If I would like to match the pattern, I would like to have inside the sine the same expression as I have in the denominator. Inside the sine, I have 3t. In denominator, I don't have the same. So, what can we do? Well, we can do some manipulations to make it the same. Well, let's give it a try. So, let me copy limit as t goes to 0. So, let me copy the numerator, sine of 3t. I currently have t, and what I would like to do, I would like to match it to this 3t. So what I will do, I will multiply and divide by 3. I will put 3 in the denominator, and I will put 3 in the numerator. The 3t in numerator will match the sine of 3t, and that 3 will be as an additional factor. Okay, so let me take that 3 and bring it outside. So I have 3 over half, and I have a limit of sine of 3t divided by 3t, and as t goes to 0. Now, I already have my pattern. I have the inside the sign is the same expression as the denominator. The only thing that doesn't match is this t goes to 0. But here I can do my favorite trick. And when you solve the examples, you don't have to really go through all of the steps, but I would like to be very careful here and justify every step of the way. So what we're going to do, we will introduce y equals 3t. And notice that y goes to 0 implies that t goes to 0. Well, because t is equal y divided by 3, right? If y goes to 0, t will go to 0. And vice versa. If t goes to 0, it implies that y goes to 0. So what that means is that every time I see 3t, I can now write y. Let's take a look. So I have 3 halves, then I have limit, then I have fraction. Every time I see 3t, I will now write y. In the denominator, I see 3t, I will write y. And the limit as t goes to 0, I can replace with the limit as y goes to 0, because t goes to 0 and y goes to 0 simultaneously. So I'll put y goes to 0. Now I have a clear match to the special trigonometric limit, and I know it's 3 halves times 1, which is 3 halves. So let us take an additional example. We have a limit as x approaches 0 of the following fraction: sine x divided by x plus sine x. And again, since we have a mix of polynomial and trigonometry, we need to use special trigonometric limit. And that limit is limit as x goes to 0 of sine x over x equals 1. Now, I don't see that limit right away in this expression. It kind of looks similar, but not the same. So is it possible to take that expression and convert it to a form where that limit is clearly popping out? And the answer is yes. It's actually fairly simple. What we need to do, we need to divide both numerator and denominator by x. Let's take a look. When we divide both numerator and denominator by x, in the numerator we have sine x over x. Well, that's a perfect match. Now, when we distribute this x in the denominator, we'll have x over x plus sine x over x. Okay, we are ready to make a conclusion. By the special trigonometric limit, this will go to 1, this will go to 1, and that will cancel to 1. So I have 1 divided by 1 plus 1 equals 1/2.